Good afternoon, everyone. We're about 1 minute out from start time, so you can see there's lots of people joining, so that's good news. And we might let it go a little bit longer than a 1 o'clock start, so that everybody can be on board. Well, good afternoon, everyone. It's just past 1 o'clock, and I think we'll get underway. Before we begin, I'd like to acknowledge the traditional owners of the land on which we meet today. In my case, here at Curtin University, it's the Noongar people. I recognize their continuing connection to land, water, culture, and pay respects to their elders, past, present, and emerging. For those who don't know me, my name is Brent McInnes. I'm the director of the John DeLater Center here at Curtin. I'm also the coordinator of the AuScope Earth Composition and Evolution program, which supports the AuScope Geochemistry Network project. One of the activities that we have under the AGN is the webinar series. We've had 5 webinars so far. This is the 6th, and today we're excited to have Derrick, Hasterok, Jackie Halpin, and Matthew giving us a presentation on the global whole rock data system. And our ultimate goal is to create AusGeochem, which is a open access data repository, which will have geochronology, thermochronology, isotope geochemistry, and hopefully whole rock geochemistry data. So without further ado, I'll introduce Derrick Hasterok, Jackie Halpin, and Matthew Gard to give the presentation.
Hey, thanks, Brent. I'll just share my screen now. And bring up the presentation. Okay, if you can't see this, just let me know. So this is sort of some work that I've been doing over the last, I don't know, I think I started this about 3 or 4 or 5 years ago, something like that, with a sort of a summer student. And it just sort of grew from there as we sort of were trying to do one more thing onto what we were doing. So we're actually going to be talking about 2 separate databases today. We're going to be talking about the Global Whole Rock Geochemical Database, which is the one that Matt Gard and I have mostly been involved with, and Jackie's helped us a little bit with the Antarctic data. And we're also going to talk about the PetroChron database, which is an Antarctic devoted database to geochemistry. And most of the names that are on here are actually part of that initiative as well. So I'd just like to acknowledge our funding sponsors, the Australian Research Council through a couple of grants, Matt's supported by a government scholarship. And I'd also like to thank all the numerous colleagues that we've had that have sent us data when we've sent emails pleading for their data sets. And I'd also like to thank the entire geochemical community for basically going out and collecting all of this data. Because without it, there's no way that we would even have such a useful tool. So the reason why we got into both of these databases turned out to be the same motivation, and that's basically about radiogenic heat production of the crust. And that is, so almost every process within the crust is dependent on temperature in some way, whether it's metamorphism or melting or chemical diffusion, petroleum maturation. I can go on and on. And so in order to understand all of these processes, we actually need a better understanding of the thermal state of both the crust and the lithosphere. So the variations that result in these temperatures in the lithosphere and heat flow that we measure at the surface come from 2 sources. One is primordial heat from the mantle, both from accretion and radiogenic decay. And then through the conductive lithosphere, it's mostly an addition due to radiogenic decay. So our understanding of radiogenic, basically the distribution of radiogenic elements is actually pretty poor within the crust. So you can see on the right here, I've got a sort of a geotherm model here. This is just one for 65 milliwatt per square meter geotherm. And you'll see here temperatures, we're looking at temperatures as a function of depth all the way down to 250 kilometers, or about the deepest extent that you would find the lithosphere. And I've computed here for a range of geotherms. And for each of those geotherms, whether it's sort of an intermediate composition, mafic composition, or felsic composition to the lower crust, I have computed sort of a range of geotherms based on the uncertainties that we have in heat production for those different rock types. And you might notice that there is actually quite a large uncertainty then in the MOHO temperature that may span a couple hundred degrees, and also uncertainties in the lithospheric thickness that can be on the order of tens to almost 100 kilometers, depending on our uncertainties. And so it's really important to understand both what the composition of the lithosphere is and heat production so that we can get estimates of temperature right. So heat production is predominantly a geochemical phenomenon. It's created by the decay of uranium, thorium, potassium. And because it's dominantly a geochemical phenomenon, and one that's trace elements at that, we want to try and remotely sense it, but the problem is we can't sense very deep within the lithosphere as a result. We can only sense about 30 centimeters from a typical measurement. So you can see in the picture here, I've got a gamma ray spectrometer, and that's not going to see any more than about 30 centimeters deep into the crust. The reason being is basically the crust itself provides shielding for the radiogenic decay, and it just can't record the gamma rays that come out of the Earth. So we actually get really poor uncertainties then, or really poor estimates of heat production if we're talking about heat production versus depth, or even heat production sort of in a large regional framework. Typically, heat production is collected in small numbers, conjunction with heat flow studies. And as a result of that, there's sort of poor spatial and temporal resolution in heat production. So these are problems that we really want to try and solve. And when I say that things are sort of poor, you know, when people are making these heat flow measurements, they often will only record 3 to 5 sort of samples from 3 to 5 sort of units that might be expected in the borehole. So our uncertainties are actually pretty large. So that brings us to geochemical databases and what they can offer for improving estimates of heat production. So there's a number of things that they can do for us, but one of them is actually giving us the ability to see these spatial and temporal variations. We can use the databases in conjunction with other information to learn about either the process controls or the tectonic imprints that result from processes like fractionation, metamorphism, metasomatism. And then it all brings us to the real question: can heat production be predicted? And I would say that was something that most people tend to have extreme skepticism about. But hopefully through a few slides that you'll see scattered throughout this presentation, you'll start to see that we think that it actually is predictable. So this plot here is actually one looking at the mafic and felsic heat production of individual volcanic arcs. So each one of these is a different arc segment. And we're looking at both of these on log scales because that's how much heat production varies. And you'll notice that most of the heat production between arcs, whether it's low mafic heat production or high mafic heat production, there's a fairly reasonable correlation with high felsic heat production. So mafic rocks and felsic rocks in the same terrain, in this case, in terrains that are result from volcanic arcs, tend to show a relatively nice correlation. And that does sort of suggest that we can start to predict heat production, at least in some environments. Okay, so the other question you might have then is, all right, well, why develop a new geochemical database? Because you can get a lot of this data already through EarthChem and Georock. And there's a few reasons for that. One is that, there's several actually, but one is that the provinces that Georock has defined aren't clear. They tell you they might tell you what geologic province the rock is in, but they don't tell you how it's defined. So it's very difficult to know whether, because there's different definitions that people may use, it's difficult to know which definition they've used and to make sure that you sort the rocks properly based on that. Some of the EarthChem databases actually don't get updated anymore. They were created once, put online as part of an NSF grant, and then were never updated as a result. And so EarthChem sort of still searches them individually as if they could be continually updated, but they often aren't. Georock is itself updated, but it's not updated very often. And it's also, the data set's also fairly biased. It's biased by mostly the data that went into it to start it. And that was a lot of data from the oceans. Most of the data are from young terrains, and it has a strong bias towards North America and sort of the Andes. The other thing too, at least from my perspective, I'm actually trained as a geophysicist, not a geochemist. And to me, the Georock and EarthChem databases are really made more for geochemists, because you have to really know what you're getting out of it and really know how to refine the searches to get the data you want. So our goal is to sort of expand on that a bit. So our database is trying to address several of these deficiencies. We're not quite there in all respects, but we're sort of working towards them. One is that we want to have a consistent classification scheme that's based on chemistry that allows us to sort of keep some internal consistency in our database that you don't get by just taking information out of papers and dumping it in the database. We compute physical properties based on the chemistry of the rocks that are put into the database. This allows us to predict things like density, seismic velocity, or other things that geophysicists may want. We also have been developing, in conjunction with the database, a series of global shape files that have various geographical information that we can use to add richness to the metadata. And then, like I said, because we've got both this ability to add richness to these to the metadata and predict physical properties, we're intending this to be meant for a larger or a broader range of audiences. So you can find the database. It's published in the Earth System Science Data, the sort of the nuts and bolts about the structure and a bit of the statistics with the data that go with the database. The database itself is also available on Zenodo, which is a sort of a large-scale cloud storage site. It's available as a CSV for download. It's actually had quite a few downloads. I think it actually had 500 downloads before the paper was even published. So I think there is some interest in this. We've been also developing a set of codes to process and plot and do and analyze the database. And those codes are available through GitHub, or at least some of them are. And hopefully in the near future, most of the codes that we have will be released through there. And then the geographic shape files that we have that we're developing right now, I'm getting ready to publish those hopefully in the next few weeks, or to send off to try and get published in the next few weeks. And once those are published, we'll get those up probably on GitHub as well. So I'll let Jackie talk a little bit about PetroChron.
Yeah, thanks, Derrick. I hope you can hear me okay. So I guess by way of introduction for Antarctic data, if you haven't had much experience looking for Antarctic data, it's actually, it's out there, but it's pretty hard to find for your average punter, I'd say. And partly that's due to the fact that we're talking about a really isolated continent with less than 1% outcrop. So in that sense, it's a pretty niche product, I guess you could say. But there is plenty of good research being done. It's being done by geological surveys commonly, that by nations that claim territory in Antarctica. And it's also been done by sort of individual university groups and academics. But data is typically not in databases. It's in theses or individual papers. So it can't be easily shared. And that's quite different to the way the glaciology community operate. They make their data very available in international sort of, I guess they have more international campaigns and they make their data available in international platforms. So that's sort of where we're starting from with the geological data in Antarctica. It's very disjointed, and it's getting really difficult, increasingly difficult to get to Antarctica, to get more samples, to do fieldwork there. So our legacy data sets and samples are increasingly important, and making the most of that is kind of one of the motivations for this project. But we're also, one of our motivations, as Derrick touched on, and I'll come to at the end of the talk, is better understanding the thermal structure of the Antarctic lithosphere and how that influences the behavior of the ice sheet, and other aspects like the tectonic evolution of Antarctica, which is a pretty big hole in the global plate model still. And we anticipate the database will have application outside of sort of traditional geology as well, in ice sheet reconstructions, for example, in soil chemistry, and even in biodiversity applications for Antarctica. So where we're at the moment, we're getting towards the end of the design phase, and we're basically at version 1. It's been designed to be open access, and we have a draft manuscript in preparation by Guillaume Sanchez, who's led the design of PetroChron. We plan also to have a web map and interface, and that is being designed in collaboration with Tom Raimondo and his colleagues at UniSA. We've designed the database to be able to be integrated with other Antarctic Earth science data quite easily. For example, the GeoMap package of digital geology maps that have recently been released through the Scientific Commission of Antarctic Research, or committee. And we also plan to submit the data set to Quantarctica. Quantarctica is a collection of Antarctic geographical data sets that's sort of wrapped in a QGIS package or project file, that's developed by the Norwegian Polar Institute, which is a great asset. So the data exists in a format that can be used in relational database management systems, and it will be available, like the global database, will be available in CSV format as well for users to manipulate. Thanks, Derrick.
And thanks, Jackie. So Matt's going to talk about the structure of the database now.
Okay, thanks, Derrick. I'll just check. Can you all hear me?
Yep.
Yep. Okay. So first, I'd just like to talk about the database structure. The database consists of 10 subtables. We've got sample information, major elements, trace elements, isotope ratios, rock group, origin and facies, triplets, age information, reference information, methods, country, and a subtable for the computed properties. And the interconnectivity of these tables is depicted on the screen, and they're all linked via their respective ID keys. So we've taken a relatively simple approach to the subtable formats, adopting some flat file formats for the subtables rather than utilize an entirely relational database format. This leads to some data duplications in certain fields, such as rock name, but we think it's a reasonable trade-off for an easier to understand and use structure. So while this format's somewhat basic, some of the intricacies of some of the more complex database structures we've used made it difficult to utilize the information contained within. And as Derrick said, was part of the driver for the creation of our database. One particular example was when we were seeking ages of rock samples. So crystallization ages are often determined by uranium lead measurements from a suite of zircons, but it wasn't always assigned to the rock it was come from. It was often stored under another mineral analyses table or somewhere else that the online portals or the downloads wouldn't always give us. And so our database, as Derrick said, is provided in two formats. We've got a single compressed CSV, which is reasonably small, all things considered, about 150 megabyte when compressed. And we also have output each of the subtables as CSVs on Zenodo as well. The Antarctic database, PetroChron, which Jackie will talk about just after me, they've restructured their database a little bit in a way that has many attractive features compared to this first variant that we used. In the future, we envision restructuring ours probably to closer resemble PetroChron. And I believe Jackie will talk a bit about that now.
Yeah, thanks, Matt. So this is kind of, I mean, similar to the global database that Matt just described. We've tried to sort of visualize it here conceptually, rather than these aren't the tables that exist in the database. This is a sort of conceptual framework around the core domains of how PetroChron Antarctica is structured. But in reality, there's lots of linked subtables. So the geochemistry and the computed rock properties are the same as the global database. We've taken that those codes and that structure. But a key difference with PetroChron Antarctica is that we store a lot more geochronology information. So it's stored as a set of parameters, including age type, which is the isotope system, for example, argon-argon or uranium-lead. The geological significance of that age, so whether it be crystallization or metamorphic age or some other significance. The approach used to estimate the age, for example, a Concordia age or a regression. The analytical technique, be it shrimp or TIMS, etc. And what materials being dated, zircon or whole rock. And then a bunch of statistical information where that's available. So we're really sort of drilling down into the geochronology to link it to the chemistry as much as possible. We also store petrology information where that's recorded, so major and minor mineral assemblages and rock groups and types and chemical classes and so on. And another point of difference, I guess, in the Antarctic database is because the accurate location data is really crucial for making good use of geological data in general, but also specifically in Antarctica. We derive location data from the Scientific Committee on Antarctic Research Gazetteer, where if it's not recorded. So we have sort of a lookup table that can pull those coordinates out. And then we record the provenance of the coordinate data, whether it be from the SCAR Gazetteer or an external database or from a publication. They're the main differences. Thanks, guys.
So I'll talk a bit now about our workflow for the global database. Data entry uses a free-form Excel template in which we can quickly and efficiently copy in tables from online manuscripts or other sources. This step reduces any chance of transcribing errors and also means we have a folder stored locally of all the original data files in case we find any issues. We pre-process these files using a script in MATLAB, and this does things such as standardize column names and remove errant symbols and text in numerical fields. And then we use Python and PostgreSQL, and we iteratively add these to the SQL database. And using PostgreSQL, we can use tools such as PostGIS, which is the geospatial database extender for PostgreSQL, to generate QGIS geometries and other things. And a number of functions keep track of new files and last date of modification, which allows us to dynamically update the SQL database as we add new files. One of the issues with this setup currently is the updates are quite infrequent and manual, driven largely by our own personal research interests at the current stage. And of course, managing and working on the database of this size is a significant amount of work. So we floated ideas such as pushing for a larger community-driven effort, perhaps an online web portal or dynamic uploads, and setting up automatic rebuilds and updates of the database on a more regular schedule. We have found CSV exports have been quite popular though, and as I said before, the compressed file format is only around 150 megabyte. Additionally, the freeform Excel template we've used to clean up data has proved to be quite useful. So just on the screen here, we've got temporal and spatial distributions of the data that are in our database. So the database is constructed from a number of sources. Some of the major ones are depicted in the figures here. EarthChem and Geochemical collectively account for more than 700,000 of the samples. And most of the rest are from the geological surveys of various countries at the time of compilation. Data from literature, which is the ones that we've compiled, accounts for around 86,000 samples, which is far fewer than EarthChem and Geochemical, but it fills several gaps in time, as can be seen on the figures on the right, as well as important gaps spatially in the figures on the left. Some of these data are associated with major elements. Some are only limited to trace, and others might just be geochronology. So it's a whole range of different data types.
So I'll talk about the geographic metadata now so this is mostly in development and has not been formally added to the database yet. So we have been using sort of rudimentary forms of this in some of our work, but this is where we're going with this. One of the reasons to do this is basically we want a polygon to define the boundaries of either geologic provinces or plates or whatever. And it needs to be, and one thing is it can be difficult to know in other databases what definition they're using. And so we wanted to make sure that we're using a common definition. And that, of course, assumes that even the other databases would have even used the same name for the same region, or different papers would use the same name for the same region. So some might use sub-provinces as well as different names. So again, we want to try and standardize that sort of thing, whether that's like, for instance, the Capvel Craton, which is a sub-province of the Kalahari Craton. And the other thing that we want to do is to provide users with this. So we want to provide users with this common definition, but we also want to develop a set of shape files that people can use in their own work, not just know that there's a common definition that's used to define the metadata in the database here. And there's a number of layers that go into this. So this is an example of just a bunch of plots that I put up that show the way the database is constructed, or at least some aspects of the database are constructed. So the database, you can sort of see the background plate model that's in there. You can see the plate boundaries colored as well. But this has a number of different information that goes into this. We're using GPS data to help us define what's a deformation zone and what's a rigid plate. We can use the locations of volcanoes and earthquakes. We use magnetic data and other geophysical methods. We've got a global gravity map. We're using global topography, global topographic gradients. We use the seafloor to help us define the ocean continent boundary, and then we refine all of these things that have been done before. We also have a number of geologic provinces that we've defined. So this is really the most useful part for the for the geochemical database. And as part of this too, we're also georeferencing a number of figures that are published in papers that show other authors' interpretations of the geologic provinces of regions. And we use that sort of as a starting point, and then we take that, we go from there and then to the geophysics to refine the locations of all of these positions. So at the moment, we're nearly done with all of this. Here are a few examples of the types of layers that are involved in these geospatial shapefiles that we're putting together. We have the ocean continent boundaries here. We're looking at oceanic domains. So this would be chemical domains that are within the ocean or created the ocean floor. This actually needs to be checked against the database. So these are chemical domains that other people have sort of defined, and we need to refine these with the actual database itself. would be sort of a novel thing that sort of gives you a feedback between both the database, the geochemical database itself, the shape files, and then those shape files go back into providing that metadata back into the database. Like I said, we're also doing plate boundaries. So this is a plate boundary map. This is updated from Peter Bird's 2003 map. And it's a little bit more accurate in some places. It also has a number of deformation zones that didn't exist in his map. So there's some definite improvements there. And then, like I said, we have the geologic provinces, and the geologic provinces also have an additional layer that tell you about the type of geologic province. So you've got the name, or you've got the province type, and a few other things as well. So we can use this information then, like I said, then to process the database. We could, for instance, take all the volcanic arcs here and use that to select all of the data that have been generated from volcanic arcs. Now, we don't envision these being completely static. We expect to sort of update these through the years as, you know, our understanding of the geology or the tectonic history of these regions has changed. And then we can use that to go back in and fix the metadata in the database. So one of my authors, Martin Hand, likes to say that I'm painting the biggest target that he's ever seen on my forehead as a result of this. And that's because one would expect that these databases these tectonic models are going to stir up a lot of controversy, because I'm going to be choosing some model that someone else doesn't agree with, and everyone has their favorite position to draw the line wherever they work. So something I'll have to worry about when I'm trying to publish this. So now I'll talk a little bit about the rock classification that we have in the database. So we're using a standardized classification system. It's hierarchical as well. So we've got a few terms in there. One is whether it's a material. If it's a null, we assume that it's a whole rock. Otherwise, we give it some designation. We also have a rock group that defines whether something's at the largest scale, whether it's igneous, metamorphic, or sedimentary. Then from there, we go to rock origin. And rock origin divides each of those rock groups into a few different categories as well. For metamorphic rocks, it's actually probably the most important to know whether it's metasedimentary or metaigneous, metaplutonic, etc. But in a lot of cases, we don't actually know that information. You can see that more than half the data don't have that information provided with them. We just know that it's a metamorphic rock in the database. I guess one other thing to note too is that if you look at the distribution of rocks globally within the crust, and what we sort of expect or can model them to be, we expect that we have some distribution of rocks through the crust that looks something like this with depth. And you'll see that 90% of the database is plutonic, or sorry, not plutonic, but igneous. And igneous is actually a relatively minor fraction of the crust, most of it being metaigneous, so it's still igneous in some capacity. But this model, for instance, doesn't separate out metaigneous or metasedimentary. These are the types of things we would want to know so that we can sort of work on how does the chemistry change with depth. To sort of fill that void in the metamorphic rocks, and whether it's a igneous rock or a sedimentary protolith, we've been exploring machine learning methods. We've been doing this with only 9 major oxides as predictors. And you can see the results on the validation data set for igneous rocks that are misclassified as sedimentary here, and then for the other table as sedimentary rocks that have been misclassified as igneous. And so this is basically the poor performance of the data set. And you see that most of the time we're getting better than 10% accuracy, or better than 10% misclassification in the igneous rocks. So we do pretty well in igneous rocks. The counter examples there are these quartzolites, which are basically quartz veins that are in either igneous or, in volcanic or plutonic rocks. So they're basically quartz veins. They look a lot like quartzites, so you can't distinguish them from that. The other are carbonatites and sort of silicic carbonatites. These rocks themselves actually look a lot like dolomite or limestone, marble, those sorts of things. And so as a result, the database does a very poor job of classifying those. But for most rocks, and most rocks in the database, it actually does a pretty good job. For sedimentary rocks, it does a pretty good job, except for a few here. The ones that it has the most trouble with are these iron-rich shales and the arkose. So arkosic rocks are compositionally very similar to granodiorites. In fact, they're basically just disaggregated granodiorites. And one of the things that one of the reviewers actually said was that he was really impressed that we were able to even get this sort of accuracy for these types of rocks, because they are so similar compositionally to the igneous rocks that they're derived from. On the right here, you can see sort of our estimates of the how accurate we are when we do these on the whole data set. And you can see that for the most of the data set, we're actually pretty accurate. We're better than 10% for igneous rocks and about 12% for sedimentary rocks. And we can use this information and stick it back into the database. Now we keep this as a separate field, so we have an estimated protolith as well as the rock origin, which actually contains the true protolith if we know it. We also use a common classification system, chemical classification system for the rock types. So if you've ever tried to look at different rock types that are in papers that are given by the authors, which is what most databases tend to include, they are relatively inaccurate because they're based on field estimates, often of modal mineralogy, or whether it's an igneous rock based on maybe its color or what they think it's come from. So the accuracy can be pretty poor in terms of those types of names. The other thing is a lot of author-defined names include modifiers that make it a little bit harder sometimes to search for different rock types. And there are a lot of different rock types that people use that may not be very standard names, or they may be standard names, but they're sort of obscure compositions. And so what we wanted to do was sort of standardize this a bit, so it was easier for users to find what types of rocks they were looking for. So to do that, we use just chemical definitions. That gives us a constant, like I said, a consistent scheme to define these names. It also helps us to filter the data set a little bit more efficiently. And for igneous rocks, because we're using a chemical classification rather than a mineralogic one, it also allows us to directly compare volcanic and plutonic samples. The classification systems are relatively simple. We're using a modified IUGS classification system for igneous rocks, for both plutonic and volcanic rocks. So this is a TAS diagram with the fields that we're using. The ones above 0 here on the vertical side are, in the vertical side going up are what we use for the low magnesium igneous rocks, and then below, on the lower side of 0 here, we would use a different classification for high magnesium rocks, and we've blown that up over here on the right. For sedimentary rocks, it was actually very difficult to find a chemical classification system to start with. Once we found one, this is the one that we actually kind of like. One of the reasons why there's not many chemical classifications of sedimentary rocks is because a lot of times that's not the important thing that people want to know when they're looking at sedimentary rocks. Often people use a quartz feldspar lithic sort of definition, or grain size. Often that information may not be included in the papers in which they give the sedimentary rocks names. So we wanted a chemical classification system that was at least easy to compare one rock to another in terms of chemistry. So the geochronology is actually really useful really important for understanding the geochemical evolution of rocks in the Earth. And so, of course, we would be remiss not to include the geochronologic information with our data. So here's a map of the distribution of rocks and its ages in the database, and you can see that most of the rocks in the database are very young. And that's because the people who put together GeoRock in the first instance were really interested in modern day rocks, especially ones in the Western United States and the Andes. So we've made the effort to try and expand this into sort of broaden the distribution of ages, of ages in the database, as well as spatially infill as much as we can. So when we sort of targeted our data collection, we tried to target regions that were gaps in the global databases. There are some significant uncertainties, though, that we have in our ages. A lot of the ages, most of the ages, in fact, have only min or max dates with them, but not a sort of a mean date or a median date and a standard deviation reported with them, like you would really want, but we'll take what we can get. And so this is sort of the distribution of the uncertainties then that we have in the data set. And you can see that most of the data that do have proper dates, most of them have uncertainties less than 40 million years, but there's still a significant fraction, about 20%, that have uncertainties more than 40 million years when we only have a min and max. So some of those min and max are based on rocks that are either nearby or rocks that are structurally, sort of have some structural relationship that give you some bounds on the ages. So Jackie's going to talk about a bit about the PetroChron ages and the way they've done it, and they've done it differently. We actually really like the way they've done it here.
Yeah, thanks, Derrick. So I mentioned before that we have a lot of geochronology parameters in PetroChron Antarctica. So just a few examples here. It's a bit difficult to see at this scale, but for a given sample, our configuration can support data from multiple isotope systems and minerals, and those ages can potentially record different geological significance. So it could be important depending on the research question. So, for example, on the left, that plot shows crystallization ages. I think they're actually just zircon ones in the database, and so they would be predominantly uranium lead, but there may be some other isotopic systems in there as well. In the middle panel, we have metamorphic age data. And so that's mainly monazite and zircon, but also some garnet ages in there, and garnet and whole rock. There's a key on the bottom right there. And then on the far right is a map of what you could term cooling ages. So that's isotopic systems such as potassium argon, argon, fission track, across multiple minerals and whole rock, as shown in the key. So we have the ability to show different types of ages.
Okay, thanks, Jackie. So as part of this database too, like I said, it's not just the database that we're sort of developing, we're also developing a set of codes that go in tandem with this. So at the moment, we've written about 80,000 lines of code in MATLAB, and these codes do everything from process, characterize, and make predictions about the database, some of which get fed back into the database and then have been published as well. And we also wanted to develop a number of routines for flexible and rapid plotting of the data set, and that's so that we can really quickly sort of explore some of the work we do. All right, but of course, we would like to move this in the future towards a more Python-friendly framework, because that seems to be the way that a lot of scientists are moving. So in the future, we'd like to have Python versions of the codes as well. But of course, in order to do this and to continue to develop this, we're going to start to need some serious money and personnel. Another thing that we do as part of this database, which is, or at least with the codes, is a little bit different than some others that you might be familiar with, and that's we include our below detection limit values as much as we can in estimating statistics or making plots. So a lot of papers handle below detection limits improperly, and that leads to biases in either statistics or interpretations. Now, it turns out in our database, we have so many data that if you're viewing things globally, the below detection limits are more or less insignificant. There's not enough of them. But if you were looking regionally or locally in different places, you would find that there are actually some places that have a lot of data that fall below detection limits. And so then you need to take some of these more robust statistics into account. We also predict a number of physical properties as part of this database. So we do density at the moment, P and S wave seismic velocities. We also do thermal conductivities and heat production. So heat production is sort of a geochemical one as much as it's a geophysical one, but I might lump it into this as well. So all of these values are also included in the database. Some of them are calibrated based on laboratory work that we've actually done, and some of them are based on thermodynamic estimates that have been made by other, or have been computed, but then calibrated based on other observations that people have done. So this is an example here looking at the density of several different rock types. So we have a few different models that we have to estimate the density of rocks. The one here that you'll notice that doesn't work very well, I'm using the same one that does low magnesium igneous rocks here to estimate high magnesium volcanics. And it doesn't work very well. When you look at the one-to-one plot, you'll see that there's the greatest deviation in those. And that's because most of these samples have actually been serpentinized. So the densities of them prior to serpentinization were probably closer to what they plot here, but that's just sort of an aside. Like I said, we're also making a number of, we also have a number of functions that plot the data. These are just a few of the examples of the types of plots that we can make out of the database. So as opposed to most of the plots that I show, I post-process a lot of my plots. These are not post-processed at all. So this is the raw plot as it came out of MATLAB. And it's just showing you the different types of plots we can make. We can look at ratio plots. We can do this in log or linear space. We can look at one ratio versus another. We can look at a ratio versus just one element. We can change the colors and symbols of these, and we can do all of this in basically one line of code. So this is a really fast, really way to do this. And so it's really quick to change when you're trying to do sort of quick testing of ideas. We can make these Cloud City, or sometimes people call these violin plots, which are just sort of histograms that are mirrored and sort of plotted on their side. We can look at biases in the chemistry through time, just like we're looking at the violin plots here. Standard ternary diagrams, we could do this as scattered points, or we can do it with contour plots, or we can do it with these sort of colored plots here. This actually took quite a bit of work to do because I had to sort of hack MATLAB in order to get it to make the types of plots that I wanted, because MATLAB's not used to making plots and triangles, but that was kind of a fun few days to sort of make it do that. And then, of course, we can make plots of things through time. This is looking at here. We're showing the statistics on this as well. So we're looking at the median values, the interquartile range, and the 10th and 90th percentiles in the data set. We've got a number of types of plots that also will do multidimensional plots. So this one's looking at sort of a spider web or radar plot. And this allows us to look at different rock types, and you can see how the trends in chemistry evolve as you go from sort of a more mantle type rock through more mafic to more felsic rocks. And you can see the progression of chemistry in all of the different elements that you might want to look at. You could do this in trace elements as well as major elements. And you could do this in physical properties as well. So what you send to the plotting routine can be just about anything. The other types of plots that we make are the pretty standard spider diagrams. This is a spider diagram that allows us to, we can send different data sets to it, and it can sort of bin those data and make the plot all at once. So again, this is sort of one code, or one line of code made all of these plots, and allows us to look, in this case, at the progression of trace elements through time. Yeah, so this is actually really, I think this one actually really excites me because we see a big change in the chemistry at about 2 billion years. And so I've got this plotted here. We're looking at the oldest rocks here, around 3.8 billion years, up to present day, which is that black line. And you can see that the chemistry sort of goes up in almost every element and then comes back down to the present day value. So this is just sort of a mini case study involving the database. This is some work that Renee Tamblin's been doing with me and Martin Hand. And what she's trying to really figure out is there's this gap in cold metamorphic rocks through time that sort of happened right around 1.8 billion years. So about 1.8 billion years ago, you start, or about, sorry, 2.2 billion years ago, you start producing these eclogites and blue schists. So these cold rocks that are related to subduction. And about 1.7, 1.8 billion years ago, they disappear, and they disappear for about 1 billion years, maybe a little bit more, before they show up about 700 million years ago, and then have been there since the present. We were trying to figure out why that was the case. If we look at about the same time at igneous rocks, in almost all igneous rocks, there's a change in the chemistry about 1.9 to 2.0 billion years. So somewhere in that period of time, there's a change in the chemistry, and it's a fairly dramatic change in the chemistry at that time. That also happens to be about the time that Nuna and Columbia, or Columbia, whichever you want to call it, the supercontinent is starting to assemble. And as it's starting to assemble, you get this big change in chemistry. So most of these rocks are probably going to be arc related. The other thing we want to do too is take these rocks and look at what's happening to these rocks, whether they're juvenile rocks or whether they're just reworked. So we can look at each of these regions and try and determine what is going on in each of these regions during that time. So this is a plot that's been made from the database looking at the geochronology. So we take the geochronology and we're making it's a histogram, but it's plotted as a color. So it's looking at the probability. The color is plotting the probability of each one of those histograms. And so each histogram going across is a single geologic province. And then I've sorted those geologic provinces by their oldest age. And I've also scaled them vertically based on their the area of that province. And the idea there was that by doing so, we get a model for the growth of continental area with time. And you'll see that the growth in area with time, it's actually not terribly different from some of the global models of that you would get from just zircons themselves. There is a big peak that happens around 700 million years, and that's probably because most of these are young rocks that haven't been eroded. And if you looked at most of the terrains that are older than that, you would see the eroded guts of those terrains that really, so I think that things older than about 700 million years are reasonable to look at here. But the main point of this slide is to really show that there's a big increase in the crustal growth about 2 billion years ago, maybe a little bit after 2 billion years ago. That growth in crust corresponds to a change in the global chemistry. And this particular, the strontium over yttrium ratio, is one that people use to suggest that there's a change in the depth of melting, or could indicate that there's a change in the thermal gradient. In this case, we think the thermal gradient is increased as a result of continental insulation from this growth of the crust. And that growth in continental insulation has heated up subduction zones. It's now made subducting plates weak, and that allows subducting plates to now break off cleanly, which prevents the formation of blue schist terrains. And so we think that there's a whole story that you can find using these sort of global databases like this. Okay.
Yeah, just go through this quickly because it looks like we're running short of time, but we alluded to earlier that the PetroChron Antarctic, one of the motivations for that data set was to look at heat flow and thermal parameters in Antarctica. And that's because heat flow is a really important parameter in controlling how the ice sheet flows and behaves. So because it's very difficult to drill in Antarctica and the limited outcrop, the way we would traditionally measure heat flow, geophysical models are typically used, and there's some examples there on the left of magnetically derived, seismic derived models. And you can see that, well, first they're too homogeneous to really be believed, I guess. And also there's huge differences between them. So the panel on the bottom right shows a difference between the magnetic and seismic models, and you can see that there's large differences. In the top right is a very new model, hot off the press, from Tobias Stahl, who's a recently completed PhD here at UTAS, who uses the global database, the geochemistry there, and he uses a similarity approach, and he draws on a diverse set of global observables and how they link to heat flow. So that's pushing in the right direction for integrating heat production. Derrick, the next slide, please. So where we're going with that, with PetroChron Antarctica, is we're doing further work to try and to bring that geological heterogeneity that we know is there in the crust and bring that into the heat flow models. So just some examples there of some plots that look at heat production. Thanks, Derrick.
Yep, thanks, Jackie. So we are getting kind of over time, so I'll just go through the last couple just really quickly. So one thing we want to do is we want to, going forward, we want to improve the structure of the database and its distribution, and hopefully get some community contributions that can really add to this database and grow it in a way that makes it sort of not just a useful resource now, but a continuing and more useful resource going forward. Some of these additions to the database that we might want to add, things like whether or not igneous rocks have had inherited zircons. That would allow one to estimate zircon saturation temperatures, for instance. We might want to include pressure and temperature conditions of metamorphic rocks. That way we can develop maps of exhumation at the surface, or at least present-day exhumation at the surface, so that we can then use that to develop models of the chemistry with depth. We want to increase the number of xenoliths that we have in there so that we can get a little bit more of a mantle and lower crustal feel that we don't really quite have from just making surface estimates. And then, of course, we want to add perhaps maybe a few more site observables with the elevation, crustal thickness, and things like that that might actually in some ways be correlated with the chemistry. So in terms of adding things like the pressure temperature estimates, if we have those pressure and temperature estimates, it can allow us to do things like develop this pseudo depth or pressure versus heat production estimate for the fjordlands, and then gives us a way to try and reconstruct the thermal history of the crust. It'll also help us resolve some issues, because if you look at the global data set actually has much higher heat production estimated for similar rock types than as predicted by global geochemical models. And these global geochemical models involve things like lean on things like estimates from xenoliths to help make those predictions. So just the very final thoughts. We think that if funding agencies and journals sort of required authors to submit their data to repositories and databases, that would sort of be one way to grow this database, perhaps in particular. And a lot of funding agencies and journals are actually starting to do that, so that's fantastic. Another thing that could really help is if journals started having standard formats to certain types of tables. So if you had a table of geochemistry, it would have a sort of a standardized format that would include the location of each sample, the sample number, perhaps the maybe some of the metadata that go with it as well that are really important for understanding that sort of sample. And the other thing too is that authors need to include all the samples that they collect in these tables, not just representative ones, because I can't tell you the number of papers that I've read where people say, here's this table with the number of representative samples, which might be 5 or 10 from a study that may have collected 100 or 200 or 300 samples. So here's a number of publications that have been written based on the database. So most of these are associated with us in one way or another, but hopefully going forward, we'll start to see people use this database that aren't associated with us and sort of the larger geologic community, the geochemical community. And any questions? Thank you very much.
Thanks, Jackie, Matthew, and Derrick. It's a comprehensive work of global scale and demonstrates the power of large data sets in understanding Earth processes. It also demonstrates the value of the community coming together to share data. So on behalf of the 40 or so people that have been watching today, thank you very much. And we're open to questions.